In this video, we will move on to our next convergence test. Recall the typical question we are going to counter is given some series, determine whether the series converges or diverges. Furthermore, the four convergent tests that we have encountered, the integral test, comparison test, limit comparison test, and ratio test, which are all designed specifically for series whose terms are all positive. We are going to move on now to include series that have some negative terms. Specifically, we are going to investigate alternating series via the alternating series test. So an alternating series is a series whose terms are alternatively positive and negative. So for a simple example, consider minus 1 to the n divided by n. If we write this out, when you plug in n equals 1, you'll have minus 1. N equals 2, 1/2. N equals 3 minus 1/3. N equals 4, 5, and so on. And we see this as an alternating series because the terms are alternating negative, positive, and so on. And if we have an alternating series, which typically we can recognize from the presence of minus 1 to a power, and note that minus 1 to a power could be minus 1 to the n, or it could be minus 1 to the n plus 1, or it could be minus 1 to the n minus 1, or so on. But something in there to make the terms alternate between positive and negative. What we will typically do is identify what is the piece left over from this. So we're thinking the b sub n is going to be our indicator. We need the b sub n to be positive. And if it satisfies the following, it has a limit of 0, and it is decreasing. If those two things are satisfied along with the b sub n being positive, then the series is convergent by the alternating series test. A couple very important points to make here. The alternating series test only can tell us if a series is converging. It will never have an outcome of divergence. But let me make the following observation. If that first bullet is not satisfied, that is to say the limit as n approaches infinity of b sub n is not equal to 0, then we can conclude that the series diverges. It's just the reasoning behind why it diverges. So then the series diverges, and the reason it diverges is the test for divergence, which we've encountered earlier in our series of videos. Additionally, similar to the integral test estimation property, if one knows that we have a convergence alternating series, we want to use S sub n to approximate the sum of the series. So recall once again the idea is that if you add up the first n terms, that does give you an approximation to the sum of the series. The question is, how good of an approximation does it give you? Well, the difference between S and S sub n is what we define to be E sub n, the error associated with that nth partial sum. And that error associated with the nth partial sum is bounded above by the next term in the series. Let's look at a few examples. So two things here. We want to use alternating series tests to determine if the series converges or diverges, and if it converges, estimate the error associated with S9. So for the series that we have here, b sub n is 1 over n, which is certainly positive. And in order to get convergence by the alternating series test, we need to check two things. The first is we need to evaluate the limit as n goes to infinity of b sub n. And the value of this limit is 0. The second thing we need to check is to see if the b sub n is decreasing. One way we can do this is to write down an associated function and calculate its derivative. Or alternatively, we can just compare the two terms. So in this case, bn plus 1 is 1 over n plus 1, and b sub n is 1 over n. And as mentioned previously, when we divide by something bigger, what we get is something smaller. So all three conditions that we need to be satisfied are satisfied. The b sub n is positive, its limit is 0, and it is decreasing. So by the alternating series test, which we will typically abbreviate with AST, the alternating series converges. Now we're going to take this a step further just to see how this estimation property works. So we want to know that since it converges, if we add up the first 9 terms, that's going to give us an approximation to the sum. Now I don't want us to go through and do that. It's really just an exercise with the calculator. But what we do want to observe is that the error associated with this is less than that next biggest term. So that would be less than b sub 10, which in this case would be 1/10. Okay, so let's look at a second example. So based upon the form of our series, minus 1 to the n minus 1 times a positive quantity, we very clearly have an alternating series. So our b sub n in this case is 3n minus 1 over 2n plus 1. So to see if we can get convergence by the alternating series test, we need to check our 2 properties. The first of which is what is the limit as n approaches infinity of b sub n. Well, this is a rational function in n, degree 1 over degree 1. So we divide the leading coefficients. The value of this limit is 3/2, which is not 0. And what this tells us is that the alternating series test cannot be used. But we can say more, we can still get divergence. So what we can claim now is that the series given diverges, and the reason it diverges is by the test for divergence. And if you're ever in this scenario where it is an alternating series and the b sub n has a non-zero limit, we can immediately conclude divergence as long as we properly justify our solution.